Hi, my name is Federico Paredes Valles, and welcome to the video of our latest ICCB paper with title Taming Contrast Maximization for Learning Sequential Low Latency Event-Based Optical Flow. This work is the result of a collaboration between the Micro Air Vehicle Laboratory from TU Delft and the Stuttgart Laboratory 1 from Sony Europe. Learning to estimate dense optical flow from event data is a challenging problem. When formulating it in a self-supervised learning fashion using an events-only approach, usually we have the model whose parameters we try to optimize, a warping module in charge of displacing the input events according to the estimated optical flow, and lastly, a loss function based on the contrast maximization principle. We learn to estimate event-based optical flow by compensating for the motion in these images of input events. If we look at the literature, most methods approach the event-based optical flow estimation problem by following the next steps. Firstly, they accumulate events over relatively long windows with sufficient displacement. Secondly, they format these events as tensor representations that not only preserve spatiotemporal information, but also that are compatible with artificial neural networks. Lastly, they estimate optical flow from these representations. Despite the high levels of accuracy reported, these methods usually suffer from high latency, large pixel displacements, and nonlinear trajectories in the input windows. In this work, our aim is to exploit the high temporal resolution of event cameras to learn to estimate low latency event-based optical flow in a self-supervised fashion. Therefore, instead of integrating events in the input representations, we propose the use of recurrent models to estimate sequential optical flow from fine discrete partitions of the input event stream. The operating principle of our pipeline is as follows. The input event stream is divided into fine partitions that are passed one by one in a sequential fashion through our models. For each partition, this model generates a dense optical flow map, and the corresponding events are stored in what we call the event buffer. Once this buffer reaches a certain length, we warp the events using our novel iterative warping module that allows us to better capture the true trajectory of seen points over time, thus improving the accuracy of the predicted optical flow. Once we have an image of warped events at each time step in the buffer, we formulate the contrast maximization problem at multiple timescales to make sure that our models are robust to a wide range of optical flow vectors. From this formulation, which is our second contribution, we get the loss that we used to train using backpropagation through time. As network architecture, in this work, we use the recurrent version of EVFlowNet proposed in the literature, and we evaluate its performance through the average endpoint error and the percentage of pixels with an error larger than 3 pixels. Lastly, since our models can operate at a frequency that is faster than that of the ground truth of the most popular event-based optical flow datasets, we reconstruct the pixel displacement over the time span of the ground truth samples by adding the interpolated optical flow vectors from the multiple estimates, as shown in the bottom right. Let's now have a look at some of our results in the DSEC dataset. As shown here, our models are able to produce high-quality dense optical flow estimates despite the large displacements in this dataset. The quantitative results on the left show that our method outperforms the current state-of-the-art contrast maximization approach with a 33% improvement in the endpoint error. This improvement can also be observed in the qualitative results on the right, which show that our results are closer to those from ERAFT, a state-of-the-art method trained with ground truth. Apart from these results, we also studied the quality of the estimated optical flow at different input frequencies. As shown in this table, our pipeline is scalable to high inference frequencies with only a minor drop in performance when reaching 500 Hz. We also evaluated the performance of our approach on the automotive sequence from MBSEC. To do that, we transferred our best model trained on DSEC to this dataset. Results show that our model outperforms most methods on this sequence despite being trained in a self-supervised fashion. Please refer to our paper for additional results on the impact of iterative warping, our image border compensation mechanism, and also for a visualization of the endpoint error for models trained with multiple training windows of different lengths. Thank you very much for watching.